going to talk about GEDI, which stands for Generalized Eigenvalue Decomposition, artifacting instrument. I will get into the technical aspects a little bit later, but I want to cover first, why we came up with this, developed this kind of tool. And I think, I don't know if you guys know, but 2 years ago, there was this paper celebrating the centenary of 100 years of EEG, in which they were asking some experts about what are the current challenges with EEG and where the future lies. And essentially, they had this interview and they asked people what the priorities were, and they found that basically the priorities for progressing EEG, the top one at the moment was artifact detection and removal methods. And we all know how laborious artifact detection or removal is in EEG. There is no real sort of set recipe book, let's say cookbook, but and I usually call it the art of artifacting because everybody has their own way of doing it. And I think we need now in the age of big data and AI, we need something that is standardized and that can kind of do things on its own, hopefully. So this is the kind of current situation we're in with, finding and cleaning the data sets. And, the data science part is actually the more laborious part than the actual analysis, because the analysis part is more deterministic, let's say, in some cases with some of the biomarkers we extract and so on from the EEG. But I think in this paper, basically they talked about these algorithm-specific challenges, what would be like the wish list of a good artifacting tool would be that you don't need a reference channel, a reference channel being a sensor maybe you would put on some artifacting, creating like a muscle or eye, like EEG or artifact, that you can maybe artifact with using just a single channel. So not you don't have multiple views on the data. That it's fully automated, which at the moment, it's the jury is out on whether we have automated artifacting tools. So in that case, you need some kind of operator expertise. If it's not automated, you need some kind of calibration, and most artifacting tools at the moment are not suitable for online applications. So they're very basically computationally quite heavy. And in many cases, they're applicable to a few types of artifact that we know are kind of sort of typical, like EOG or EMG for ICA, but not all the full gamut of artifacts that are possible in, like, I don't know, MOBI studies where you're moving and recording patients. So in the ideal case, you would have an ideal artifacting removal should be online, fully automated, calibration free, easy to use, and it should be able to deal with all types of artifacts without the need of an extra reference channel. So that's the wish list. And I dare say we might be there with GEDI, apart from, nothing's perfect, that you can't do it with single channel because it's a projection method like ICA. So you need multiple views on the data, so you need more channels. But I think that's inherent mathematically in probably any good denoising technique. So I'll get straight to the point about the name of this preprint that we call, turn of the JEDI, unsupervised artifacting based on Leadfield filtering. So what is Leadfield filtering and what's so new about JEDI in terms of how artifacting is done? And in this case, we actually used this sort of forward model Leadfield. I'll explain to that what I mean. Here's a metaphor that I like to use, the so-called camping metaphor of the lead field and the filtering associated with it. So if you imagine like you're going camping and you're in a tent, and the tent is kind of like the skull, right? It has its own boundary. And if you have a brain source within this tent, then it's like, imagine it's like a source, like a flashlight. So it has a spatial location, it has an orientation as well, and it projects from inside the tent to the outside of the tent. And from the outside of the tent, you can see this kind of patterns of what the light projects from. And then you can imagine that things that are artifacts are kind of by definition, things that sources of electrical activity that basically are outside of the tent, right? By definition, because something that's not brain is outside of the skull. So in this model, again, we assume that artifacts are extracerebral sources. And then if they're from outside this tent, they project differently onto the tent as if they were from the inside, right? You can see that the pattern is different and also the angle at which it projects from. And that's basically encoded in this thing called the forward model. It's basically, the forward model is how you generate EEG data using this kind of generative EEG model. And then, you have some kind of grid, which is where the the brain is located inside the skull, and in each of these skull you have some sources, right? Dipolar sources, which you put like 5,000 of them or so on, and then you basically orient them in a forward model. You can orient them randomly, and then they basically project onto the electrons, right? So that's this Leadfield matrix is basically the channels times sources matrix, and then each of these sources have also some temporal activity. So if you multiply G by S, you get your fully reconstructed EEG data, and that's also what's behind the inverse model. It's like, how do you get from the data to the source space, right? So this is just going from the direction of the brain first. And you can reconstruct this data with channels by time. Right. I hope that's clear. So this Leadfield matrix encodes, let's say on its own, the G on its own doesn't actually encode anything about the temporal activity of the brain. That you, of course, have to have separately. But on its own, it's just a channels times sources. So it's basically a spatial model. It's how the sources within this grid project onto the channels. And if you were to plot this Leadfield matrix, well, you can see it's kind of like a flashlight, right? So you can see here, this is the flashlight that if the source was internal to the brain near this area here, it would have this kind of pattern, circular pattern on top of the electrodes. And you can see here for X, Y, Z orthogonal directions, these are the patterns it creates. So there's some negative and positive, but mainly it's this kind of dipolar patterns when the source is active, right? And essentially what you can do is you can work out from the topographic pattern on the electrodes whether sources are kind of, emanating from within the brain or outside of the brain. And how this is done is, for example, if you do a dipole fit, here's a dipole, that's kind of like a flashlight, it's pointing this way, okay, in this direction, and you can see the topographic pattern on the sensors that it would create, just like this flashlight in a tent. And if I give you some examples of dipoles that are actually extracerebral here, these are some ICA decompositions of some activities that are blinks, for example, here. This is a blink that is coming from here and so on. So essentially, those patterns are differently shaped. I mean, you can't see it with your human eye how different they are, but they do project onto electrodes differently, and they have less intrusion over more electrodes. So this kind of pattern of activity is encoded by these electromagnetic activities, right? And what you can then do is try to work out, okay, any kind of component that you can decompose in the data, in your empirical data, does it have a pattern that is consistent with a generator that's inside the tent, or is it maybe something that looks like something that can't be explained by that? I.e., it means that the generator is coming from outside the tent, this topographical pattern. And so that's encoded in this covariance matrix. The covariance matrix being essentially kind of connectivity matrix between channels. And to generate this covariance matrix from empirical data is you essentially multiply the channels by time that you have. So that's your data. You take, let's say, even a second of data of channels by time. You multiply that data by its transpose. So channels by time times time by channels. And you essentially get this nice covariance matrix that you see here. And this encodes the relationships between the channels. So channels that are close together have shared covariance. Like here, for example, and channels that are not close together, they basically further away from sharing their electromagnetic activity. According to when the brain is generating the EEG, right? This is a clean covariance matrix. And you can do the same thing as a reference with the Leadfield. And so now the Leadfield is different because it's channels by sources, but you can get to the same kind of space in channels by multiplying channels by sources by channels. And then you are basically on the same playing field, right? In this channel by channel space. And here you can see the similarity between the theoretical matrix of pure clean EEG coming only from this grid of cerebral sources and the clean EEG here. And you can see that they have very nice match, like 0.9 correlation coefficient or more. So essentially, you now have some kind of a teacher matrix, which is this theoretical matrix that can be used to create a contrast for any other empirical data matrix that coming in that might have some sources or activities components that are inconsistent with this kind of signature. And that means that, and how do we leverage this contrast between these two matrices when this matrix is slightly different from this one, is basically, that's basically this JEDI mind trick that I told you about. So you use time in the channel space of the data, and you you basically relate it to the space matrix of the Leadfield covariance. And that's, you can do that with this algorithm called generalized eigenvalue decomposition. I'm not sure how many of you have heard of it, but it's kind of like a fancy PCA. A PCA being just an eigenvalue decomposition, right? Everybody's familiar with PCA. In this case, it's so PCA is essentially this kind of model here, right? You have your data coming in, and then you create this data covariance, and from this data covariance, how channels are related to each other, you find these components, right? You find these kind of maps. There are components, for example, blink here, you would have covariance here in the frontal channels, and then if you reconstruct this spatial pattern in the time domain, you can see that this is a blink. And then it has, these are so-called encoded in the eigenvectors, the so-called spatial filters. So that's PCA, and PCA only looks at things by variance, right? The bigger components get sorted at the top. But JED additionally, what I mean is called the fancy PCA is because it basically has this reference matrix in addition to the original data covariance. And this is the magic reference matrix that we've just generated using the Leadfield. All right. And so what it does, it finds a contrast between these two matrices and looks for components that are diverging between them. And then when you get these components out, they are sorted just like the PCA components in terms of eigenvalue, but these generalized eigenvalues now actually don't just represent variance, but also direction of variance. So for example, if this flashlight is directed differently for extracerebral sources, it will have very large eigenvalues. So essentially all the most artifactual components will come up at the top, and they will be sorted all the way down to reconstruct the full data, including the artifacts. Okay, so that's clear. But if you want to know more about generalized eigen decomposition, I strongly recommend both the paper in Neuroimage by Michael X. Cohen that actually was inspiration for this work, and also a video on YouTube that explains this method that you can use in many different other approaches, not just denoising. So once you have these reference covariance and you have also the data covariance, so you then decompose it, and this is the so-called metaphor that I like to use, the oil and water metaphor. So as I said, the artifactual components have the largest eigenvalues. They kind of float to the top of this list of components. So think about these components like ICA components, but they're not randomly sorted. They're sorted by eigenvalue. So the largest eigenvalues are at the top. So that's the kind of the oil. And then at some point you have to reconstruct obviously all the data. You have some water layer, which is now the brain components, right? And then you have this threshold T here in the middle, which separates these two subspaces, so-called. So you have the noise subspace here and the water the signal subspace here. And so essentially there's another algorithm that we developed for JEDI that actually calculates this threshold. I'm not going to get into it, but you can look at it. The preprint, it's called Sensei. But essentially what you do then, you just simply separate these two layers, and you have your data in one bucket, which is just noise, and the other data just signal, right? And that's all there is to it. So I don't know, I asked Renate if she wanted the demo, so I have a few files that we can do a demo on. So I'll show you that in MATLAB. I know some of you work in Python, but the code is also available for Python and MNE, so if you want to try that. But here's a demo in EEG Lab, for which the tool was first developed. And I have a few demo files that we'll go through, like 2 or 3 if you want. One first file just to give you a flavor of what it does if, for example, here, blinks and bad channels. So in this file, if you look at the data, well, it has this obviously these blinks as well, right? These are the blinks here, which is kind of easy for ICA. But then you can see sometimes some of these channels pop out a little bit as being maybe artifacts, maybe not. We don't know here. Is this real brain activity or not? And it's difficult to tell because it's temporal lobe and so on. But you can see it's kind of popping out here. So what you do is you just press JEDI and you press OK. I'm not going to get into details, but essentially this is the Leadfield matrix that it uses that's pre-computed for most of the 343 10.5 channel locations that are standard. You can also use interpolated, which is non-standard locations that kind of warps the matrix into these like custom space. Then you have a low frequency cutoff, and so on. But essentially, it's made to be automatic. So you just press OK, and then a few seconds later, this is for 180 seconds of EEG at 61 channels. with 125 hertz. So this is now the data. Here we have a so-called ASR visualization from the ASR tool. So the red traces are the original data, which is the noisy one. So here I'm just highlighting the red stuff. And you can see here the blink. And then if we go further, you can see maybe some of these potentially bad channels, maybe not. And if you then overlay the traces from the JEDI denoise data, that's the blue underlying thing, you can see where it's red, that's where basically it's corrected the EEG. And where it's blue, it's where there's a good overlap between clean EEG and the data. So you can see in some places it hasn't corrected at all, which is kind of the clean data, which you see the oscillations. And then sometimes these bad channels. So in this case, the concept is that the bad channels are not removed on or off. It's not just like the channel is completely removed for the whole time series. So if you have like real-time data that suddenly becomes bad channel, the JEDI will detect it because the epochs for the denoising are very short. They're like half a second long or less. So in this case, for example, here it's corrected the bad channel, but then here there was some nice bit of data where the channel wasn't bad, and then it seems like it's fine. So these are the blinks. And then if you look at just the difference, so this would be now just the noise subspace. So I just subtracted, the original data minus the denoise data. This is now what's the remaining noise. You can see here this regular activity. It seems like it's some kind of noise. So and there's lack of the alpha oscillations, and then there's some also non-stationary stuff here, like some movement and so on. So that's basically one example. Now, if we go to another example, which is a little bit, let's say, a little bit more noisy, because we developed it also for very noisy EEG, which has like a lot of movement. So for example, this one here, we go straight to the denoising. This one should be faster. It's only 19 channels, so there it's for 180 seconds. It took a few seconds to process. It's pretty fast. So here we have the same principle, and you can see here we have much more noise, like movement, cable noise, whatever it is. So you can see this is like many orders of magnitude larger. So you see there, that's the original data, and then the clean data is this one. So you can see that the alpha here is hugged nicely for the clean parts. And then if you keep going, there's a lot of EMG here. So this would be like, for example, if you're recording patients, if they have some clinical disorder like Parkinson's, so on, this would be nicely removed. See there. And it's pretty strong. So it does a very good job at removing anything that isn't brain. So basically any artifact type. There's nothing in the model that says that it cannot model another artifact, because the only thing that it's modeling is clean data. So essentially any data that diverges from that model will be thrown away. So here's again the difference of the noise. So you can see here's the difference of the noise and so on. Last application I want to show you, since we have limited time, is, I'm not sure how many of you work with brain stimulation in psychiatry, but it's also potential use in brain stimulation. So here's some tax data. This is 30 channels, 400 seconds. We know that it's very challenging to denoise data during brain stimulation and find out what are the underlying sources of the brain activity while we're stimulating, right? That's the idea also of the real-time applications of brain stimulation. So here's the data set with tax. Now this is before tax. So now you can see the traditional blinks here. That's your noise kind of before tax. And then if we slide to the tax part where we turn on the stimulation. So here you can see there's again some kind of channel here, some bad channel here, blah, blah, blah. That's corrected it. Then you keep going, and then some EMG, and then finally the stack starts, I think, here somewhere. Oops, not yet. There it was. So yeah, there it is. So here there's a massive sort of, oversaturation here of the EEG. If I increase a little bit. So if we just looked at the tax, you can see there it's massive, right? It's basically overpowering all the channels at a particular frequency. I think this is kind of beta tax. And you're not going to find anything in there, right? But what's amazing is that there is something behind it. So if I overlay the blue, you can try to get to the blue behind it, right? And if we get to the blue, you can see there's no discontinuity at the transition. And you can already see some of these oscillations here. So if you go again, B, and then we go a little bit further, we can see some alpha bursts here. That to a trained eye look like oscillations, but of course it's not guaranteed that they are. That's why the second part of my talk will be about validating this. But I have done some validations also on the brain simulation data that seems to be working very well to recover the activity in simulated settings. Okay, so any questions at this point before we continue with the presentation regarding the demo, and we can do it also after. All right, so let's continue. So obviously, extraordinary claims, but there needs extraordinary evidence also to say that this is doing its job. And it's not so much about making it look nice, looks clean, but is it really clean, and does it represent the underlying brain activity? So that's the second part, which is the general challenges of validating denoising algorithms. So do you validate on real or simulated EEG data? There's a lack of public EEG artifact datasets. I know that because I've tried to find them, and there's like a few found, and we use them for these benchmarks. A lack of open source solutions. Many times they're closed as well. Special challenges of machine learning based algorithms. Yeah, that depends on which algorithms you use. So there's many, including deep learning, which requires some training data, and then that can fail to generalize. And then there's also lack of benchmarks. I don't think there's one benchmark that I know that actually includes denoising. So the remedy would be that researchers should evaluate the model on both real and simulated EEG data and open source the code and data files for reproducibility. The EEG community should also establish a competition for benchmarking the different methods. And it's exactly what we've done with this preprint. Once it's published, it will release all the benchmark data, and it can be used to benchmark other algorithms. And so here's the parts of my presentation for introducing this denoising benchmark, which we developed specifically to validate JEDI. And the way it works is that essentially we know that, brain signal, on the scalp, the EEG signal is a linear combination of the brain signal and artifacts. So, it's electromagnetic superimposition, and therefore you can create actually kind of dirty EEG by taking clean EEG that you assume is clean, and then you add some artifacts, okay? And that's using these components. So you have sort of single-dimensional time series, and you basically project them onto this multi-channel data. So this is, for example, the red trace that I showed you earlier. That's the artifacts, and then you would have this underlying ground truth, which you would want the denoising algorithm to recover, right? Without knowing what it was originally. So you basically present it only with the red, and you try to see, can you recover the blue? Now, of course, ground truth is difficult in the brain, but you can do simulated synthetic sort of benchmark. So in this case, this is part of a paper that should be published also soon called BEAR, the benchmarking of EEG artifact removal with both empirical and synthetic data sets. So this is the summary for the synthetic part. This is basically forward modeled EEG. So we know that, where the sources are in the brain, we basically forward model them. The forward model is actually non-ill-posed, not like the inverse model. So we know exactly how it should be on the scalp. And then we add, so we create some clean data with some, oscillatory activity like delta theta alpha with 1/f and so on. And then you can also create 20 artifact data sets with dynamical, I'll talk about how this is created, but you can superimpose these artifact data sets on top of this clean data, and then you try to recover the clean data. That's for the synthetic data, and pretty much the same thing for the empirical data. You take some kind of visually clean or expert cleaned data that you have identified. It doesn't contain artifacts, then you mix it in with some artifacts, and then you see if you can recover the ground truth. And then overall, the benchmark is something like 400 data sets and 200 here. How did we do the synthetic one? This is actually leveraging this nice tool that Niels Harmening created in 2002 called the Hartman head model. So most head models for EEG contain only, the gray matter space, right? And they don't actually at all take into account that noise might come from the outside, or at all take into account noise. In fact, in inverse source imaging, you have to assume that the data is clean. But in this model, actually, you see here the source grid. Here you see that. Oops. This is basically extracranial sources that can be placed in the eye. So it's an anatomical model of the full head, including sources in the eyes, in the eye sockets, as well as in muscles. And so you can basically create, you can take single channel EOG data basically of electrodes that are placed on the muscles, and this is so-called EEG denoise data set, which has single time series of actual EOG activity and EMG activity on the muscles. These are real empirical data, and you project them via these locations here onto the electrodes using the form model, and then you mix on all this data together and you try to recover the clean signal, right? So we did that, and here's the competitors. So RAW means no denoising at all. ASR is the PCA-based artifacting method, IC label, ICA-based machine learning based. So these are all kind of automated in some sense. And JEDI here at the end. And then we vary the noise sort of across three key axes, the type of noise, whether it's an EEG, EMG, or actual kind of environmental noise like line noise, or the combination. We vary the temporal contamination from 25% contaminated epochs to all the epochs being contaminated, that's 100%. Which JEDI can work with because it has this theoretical model. It doesn't need clean reference data. And you change also the signal to noise ratio. So 0 dB being the noise amplitude is the same as the signal amplitude, the background EEG. -9 being 4 times larger noise. So the total synthetic benchmark was 3,200 data sets. If you multiply all these combinations together, I'm not going to get into details. That's all in the preprint, but overall, this is the global results across all artifact types, all temporal contamination levels and SNRs. If you just aggregate all the data, you get JEDI being reconstructing the sort of ground truth at more than 95.95 correlation coefficient. So you have so that's quite much higher than the best, second performing best, which is the ICA one, and in much less computational time. And then the same thing for SNR, if you don't look at correlation, but you look at how you reconstruct the signal to noise ratio of the data. In the time domain, you have the highest sort of SNR value for JEDI. So yeah, that's overall the score for the synthetic data, but obviously that doesn't mean that it generalizes well to empirical data, because this head model might, not be accurate for empirical data. So we ran the same thing. You can look in the preprint how we did that, but on empirical data, we had pretty much the same results. We had a drop from 0.95 to 0.92, not a massive drop. This is for 27 channel data, empirical data, so it works quite well with low channels, and it's really working really well. So that's the overall global results for the benchmark. But I think the biggest question is, why do all this? Well, the point is to actually improve neuroscience and to get better estimates of biomarkers and better brain behavior correlations. So we also in the preprint applied some neurobehavioral prediction to see how JEDI might perform compared to these other tools. And for example, you can use some other ground truth data. If you don't have the actual brain ground truth data, you might know something about the task, like what kind of stimulus the person was exposed to, right? So for example, so-called single trial ERP decoding. And in this case, it's a very basic oddball task where the person watches just some white squares, and once on so often, 16% of the time, there's a picture of Einstein, and they have to press the button because that's the target. And so overall, we know when the Einstein is presented, so that's the ground truth. And the ERP basically elicits a P300, which is a much higher amplitude than for the non-target, and that's how you know that in the brain you can try to predict whether the person, without knowing it, saw Einstein or not, right? So you try to decode whether the ERP represents Einstein being seen or a white square. And so here is a data set that's open that we applied JEDI to and all the other algorithms. So anybody can do this today even. And 73 subjects with 143 trials. So overall, more than 10,000 ERP trials to decode without throwing away any bad trials, right? So we keep all the trials because we want to see how bad it is, even if the noise is really bad. And these are the overall results. Raw, you can see, is pretty much at random. So there's no way you can recover your APs with some kind of EEG in the wild data. So basically, it's a binary classification. Did they see Einstein or didn't they see Einstein? Well, essentially, it's at 50% if you don't denoise your data at all, which goes to say that denoising is very important. Then if you start to denoise, with ICA, you get some better than random here. ASR does quite well also for the fact that it's just PCA based. It's removing the large artifacts. But JEDI does, much better, significantly much better to recover at 0.8 AUC. this classification, binary classification. So that's really promising also for real-time BCI use, because that's one of the key areas that this would be used in. Another example is when you know the ground truth, you might, I don't know if you guys know about brain fingerprinting, but essentially it's like you can detect the person's identity based on their basically EEG signature. It's also done with fMRI, but with EEG can be done also. And what you do is you just take 100 subjects. You have to have test retest data. So it's not within the same session, but across different sessions. So here there's 2 separate sessions, 5 years apart. And you have a single resting state EEG recording from which you calculate the covariance matrix. It's kind of a connectivity matrix of that person. And then you try to match that connectivity matrix among all the other people. And you're assuming that, that connectivity matrix is representative of the person's identity. So if there's a lot of noise, you would kind of lose that stereotypical signature, right? And you can see this red line down the middle is essentially the person. These are the different sessions, subject ID, and you can see how this dark red line is that the subject represents is most similar to themselves. Although a lot of subjects are similar at 0.9, but that trips the threshold. So essentially, the fingerprinting finds the entry at which the person is the maximal in correlation with these other subjects. And so if it's along the diagonal, then it's 100%, right, for every subject. But obviously, it's not 100% here. So these are the results. If you take just raw data, you're pretty much at 50%. Accuracy. 25 IC label here with ASR just removing blinks in EMG is pretty much the same as raw. And then ASR does second best at something like 77% here, and JEDI at 90%. So that's really promising there, that you can recover the brain activity to identify the person with JEDI. So overall, that's my whole presentation. I hope it didn't take too long. And yeah. The plugin and the code is available in Python for M&E and also the other 3 MATLAB toolboxes, e.g. Lab, Field Trip, and Brainstorm. Thank you so much.